Welcome back, guys. So this is the third lecture of this series of FIR filter design, and here we'll learn about the design steps. So in our earlier discussion we have discussed about the we had got some general idea about what is window and what are the different window, rectangular window, then hemming window, handing window. So all these things we have learned. Now in this particular lecture we will concentrate on the design steps, how a filter can be designed from the window. So to start with, the very first and foremost thing is that we need to know the desired frequency response. This will be given to us. Okay, so desired frequency response, which is generally defined as hd of e power j omega, that is equal to e to the power minus j omega alpha for omega less than omega c and 0 otherwise. So if we pictorially represent this particular equation, then we get this equation. So this is the magnitude response, and we see that magnitude is 1 here, and this is the phase, and the phase response will be something like this. So this is what will be given to us, only this equation. From this equation we need to draw this. So this is the step 0 of solving any problem associated with the design. You should always represent it pictorially. That will give a good impression towards the examiner, as well as it is a good practice to do, so that your understanding will remain. Okay, now coming to the desired impulse response, from the desired frequency response we need to obtain the desired impulse response, hd of n. So how can you get it? We have to perform the inverse DTFT. Inverse DTFT you have to find. So for inverse DTFT, this is the relation given: 1 by 2 pi integration from minus pi to plus pi hd of e power j omega e to the power j omega n, and integrating with respect to omega. So if we see this minus pi to pi in this region, hd of e power j omega is only defined from minus omega c to plus omega c. So we are taking this limit, and within this limit we have seen the value of hd of e power j omega is e to the power minus j omega alpha, and otherwise it is 0. So we need not to consider the other part, that will be 0. So now within minus omega c to plus omega c, if we combine these two exponentials, we get e to the power j n minus alpha omega. So we are combining this, so this is n, and this from here we are taking minus alpha. So we are getting this particular expression. Now after solving this integration, what we are getting? E to the power j omega n minus alpha divided by j n minus alpha, and limiting from minus omega c to plus omega c. And if we simplify it further, we get hd of n, that is equal to sine omega c n minus alpha divided by pi n minus alpha. So this is what we'll be getting. Now interesting thing is that when alpha n and alpha are not equal, this expression holds good. But when n and alpha is equal, then numerator and denominator we are getting 0 by 0. This particular relation we are getting 0 by 0. So we have to apply L'Hospital's rule, or we can use directly this limit formula. So limit theta tends to 0, sine theta by theta is equal to 1. So this is the basic of the limit. So extending this, we get theta tends to 0, sine a theta by theta is equal to a. So it is in the form sine, this is a, omega c is our a. So this particular portion, taking 1 by alpha aside, if we take this one, so n minus alpha if we take as theta, so sine omega c theta divided by theta. So limit theta tends to 0, sine omega c theta by theta. So this is giving us omega c, and we have kept 1 by pi aside. So we are getting for n equal to alpha, omega c divided by pi. So that is the value of hd of n. So this step is very important one. Now next few things you need to note, that the impulse response of the filter, which are nothing but this impulse response of the filter. In our earlier discussion we have seen that these are nothing but the filter coefficients. So to design an FIR filter, we need to find the filter coefficient. So filter coefficient is given by as h of n equal to hd of n into w of n, and w is the window function. So for h of n to be linear phase, the delay factor alpha is the delay factor, and we need to select this alpha in such a way that we get a symmetric filter. So that is the objective of linear filter. So this sine omega c n minus alpha divided by pi n minus alpha, this is symmetric about alpha, n equal to alpha. When n equal to alpha, we are getting this 0 by 0 form, and window is symmetric about n equal to n minus 1 by 2. So that means we need to consider alpha as n minus 1 by 2. So numerical value of alpha should be n minus 1 by 2. So now if we are considering the causal filter, causal FIR filter, so here the window length we are considering from 0 to n minus 1 instead of minus n minus 1 by 2 to plus n minus 1 by 2. Here we are considering it from 0 to n minus 1 by 2. So why we are considering that? Because we are studying the causal FIR filter. We are trying to design the causal FIR filter. So now what are the design steps? First step, you will be given these things. So K1 value, K2 value, that is related to pass band or cutoff. So minus 3 dB bandwidth, K1 is representing minus 3 dB, K2 is the stop band attenuation, and omega 1 we are choosing as the cutoff frequency, omega 2 is the stop band frequency. So this diagram, once again I request you, whenever you will be solving any such design problems, please show it pictorially so that it will be easier for the examiner to understand, and for you also it is clear. The probability of error will become minimized. So here step 1, what it says, that select the window function such that stop band gain or attenuation exceeds K2. So earlier in our discussion of different windows, we have seen that each of the window is having some minimum stop band gain. So it should be more than that. So for example, if K2 is given as minus 40 dB, then we can choose the Hind window because it allows stop band attenuation up to minus 44 dB. So minimum stop band attenuation is minus 44 dB, and it has to be more than that, that is minus 40 dB. So that is how we need to choose the window. If this would have been minus 50 dB, then we would have gone for Hind window. So this is a very important thing, which window you are choosing. Now step 2 says that select the number of points in the window. That means, in other words, it will give you the stiffness, that is roll off of the filter. So points we have to choose in such a way that it will satisfy the transition width of the type of window, because each of the window they are having different transition width. So relation is omega t is the transition width, so that is equal to W2 or omega 2 minus omega 1, and that should be greater than equal to K 2 pi by capital N. So that means N should be greater than or equal to K 2 pi by omega 2 minus omega 1. Now k is a constant that depends on the type of window used. For example, rectangular window k is 2, for Hamming window and Bartlett window k is 4, and 6 for the Blackman window. So if n is a fractional number, then choose next higher odd number. That means, for example, if you are getting n equal to say 25.3, then we should not choose 26. So n we have to equate to 27. Next higher odd number. So we are basically using odd symmetry. There is even symmetry also, but that is the scope of the discussion in advanced DSP. So here we are choosing n as higher odd number, so we are going with the odd symmetric FIR filter. So step 3, select the cutoff frequency and delay factor such that omega c equal to omega 1. This point earlier we have discussed. Omega c equal to omega 1, and alpha for linear phase we need to choose alpha equal to n minus 1 by 2. Now the most vital part is coming. So we have to find hd of n, each value of hd of n, say for n equal to 0 to n minus 1. For each value of n we need to find hd of n. Same thing for each value of n equal to 0 to n minus 1, we need to find wn window function, and then element by element we need to multiply to find h of n. So h of n will be our filter coefficients. So once we get the filter coefficients, step 5, we can determine the frequency response of the filter by using this particular relation, h of e power j omega, that is equal to summation n equal to 0 to n minus 1, because within this limit we have defined. So in DTFT, though we are performing DTFT, and the range as per definition of DTFT is minus infinity to plus infinity, but in this case we are not doing so. We are considering it 0 to n minus 1, because that is where h of n values we have, otherwise it is 0. So for n odd, h of n, that is given as e power minus j omega n minus 1 by 2 into h of n minus 1 by 2, that is midpoint we are taking out, and twice of the other points. So these are given by this equation. So that is the frequency response. So you can keep it as it is with only changing this value, and the equation as it is. Similarly, this is the most important part here, the transfer function of the digital filter. So for that we need to perform the Z transform, and that is given as summation n equal to 0 to n minus 1 h of n z to the power minus n, and for n odd it is given as z to the power n minus 1 by 2 h of n minus 1 by 2 plus twice of this thing. So here you see z to the power minus n. Earlier for linear filter also we have seen this relation, that means the coefficients are same. Say we have n equal to say 5, that means n is ranging as 0, 1, 2, 3, 4. So here this is the midpoint, so that value we are taking aside. So we can write that h of 0 is equal to h of 4 and h of 1 is equal to h of 3. So this is how they are related. So once we find the filter coefficient, we can find the transfer function. So finding transfer function is the objective for FIR filter design. So here our problem ends. So for preparing this, I have utilized these references, and you can go through the reference number 4 and 5. Lots of solved numerical examples are given, and you try it of your own, and in next lecture we'll take 1 or 2 numerical examples to make you understand. So join me on part 3D. Thank you.